So I'd like to conclude this lecture on Green's theorem by presenting one application of the theory. This is a sort of more of a pure math application, but it is quite useful. So the context here says, let's say that we're studying a vector field f, and let's say that this vector field happens to satisfy the equation Green operator of f equals 1. Well, if this happens, then there's something interesting that happens if we apply Green's theorem. Green's theorem says that the work done by this vector field along the boundary of any domain is the same thing as the double integral of the Green operator over the boundary, over the domain itself. Well, if the Green operator happens to equal 1, then this is simply the double integral of 1 over the region D, dA, and we know this double integral is actually the area of the domain. So the punchline is, if the Green operator equals 1, then the work done by the vector field along the boundary of the domain is actually the same thing as the area of the domain. And there are meaningful examples here. So there are lots of different ways to choose vector fields whose Green operator equals 1. Here are a few of those examples. So this calculation that says that the work done by a vector field whose Green operator equals 1 is actually the area of the domain can manifest itself as an equation that says maybe the area of a domain is equal to the line integral of x dy over the boundary of the domain. Here we're using the differential form notation, and in this equality, what we're doing is we're choosing the vector field to be 0, x. 0, x certainly has Green operator equal to 1, since the second coordinate is x, which has derivative with respect to x equal to 1, and the first coordinate is 0, which has derivative with respect to y equal to 0. The area can also be written as the line integral over the boundary of negative y dx. Here we're choosing the vector field to be negative y, 0, which also has Green operator equal to 1. And yet another way to do it would be to say that the area is 1/2 of x dy minus y dx. And here we would be choosing the vector field to be negative y over 2, x over 2. So the idea is that whenever our vector field has Green operator equal to 1, we know that the work done by that vector field over the boundary of a domain is the same thing as the area of the domain. And 3 examples of vector fields whose Green operator equals 1 are the vector fields 0x, negative y 0, and negative y over 2, x over 2. And why is this useful? Well, sometimes the double integral over a region is actually just difficult to calculate, even if the function we're integrating is equal to 1. So, however, sometimes this work integral, which is the line integral of f over the boundary of D, that's another typo I need to fix, is easier to calculate. So let's see this with an example. So here we have an example where we're defining a domain to be enclosed by a curve. The curve we're studying is x of t equals sine of 2t sine of t, where t ranges from 0 to pi. If we were to plot this region, it isn't intuitively obvious, but it does turn out to look like this sort of teardrop region. So the idea is that we've defined this parameterized curve, which starts and ends at the same location, and then we're using that to define D to be the region inside of this curve. Well, how could we calculate the area of this region? Well, you can imagine this being a difficult double integral to even set up because, well, the methods of slicing might be difficult to figure out here because this boundary curve is defined as one big thing, not as one coordinate as a function of another. So how could we calculate the area? Well, according to our formula on the previous slide, all we really need to do is figure out the work done by any vector field with Green operator equal to 1 along the boundary of this region. One of those examples was the line integral over the boundary of this region of x dy. Well, this line integral is actually accessible because we are given a parameterization of the curve. So this line integral is the same thing as the integral from 0 to pi of sine of 2t times cosine t dt. Where do these coordinates come from? Well, the sine of 2t is the same thing as the x-coordinate of the parameterization of the curve. And cosine of t dt is what we call dy here. This is the y-coordinate of the velocity vector for the parameterization. And so now we have a Calc 1 problem on our hands. I think a trig identity is useful here. Sine of 2t is really the same thing as 2 times sine t times cosine t. So now we're looking at 2 times the integral from 0 to pi of sine of t times cosine squared t dt. And I think a u substitution is appropriate here. If we choose u to be cosine of t, then du is negative sine of t. And then if we apply cosine to 0, we get 1. And if we apply cosine to pi, we get negative 1. So now we're looking at negative 2 times the integral from 1 to negative 1 of u squared du. And this simplifies to 4/3. So the area inside of this region is 4/3, which we managed to calculate using Green's theorem.